Last class we are trying to design the speed loop using the symmetric optimization using graphical technique. There we considered the loop gain. So, finally, we got the transfer function open loop gain, we got K4 into 1 plus TNS by A square Tn Tm into 1 plus delta S. Okay. Now, from the control system theory, we know that one condition for stability is that the loop gain of the system should cross the unity gain with minus 20 dB per decade. So, let us draw the frequency gain of this one. If you do it, F0 omega, this is our log omega, this here it is our gain, and this pole at delta, that is 1 by delta, this we know it. Choose Tn from the last example, we know it Tn is equal to 4 delta. Okay. So, 1 by Tn will somewhere here it will happen. Now, till this corner frequency is approached, this S square is the dominating factor. So, it will come with minus 40 dB per decade. Then the 0 will come, 0 will make it minus 40 dB, it will give a lead, and then finally it will give to minus 20 dB per decade. So, we choose Tn such as sufficiently away from delta. Once it comes to 1 delta, again minus 20 it will introduce. So, minus 20 again minus 20 again it is parallel to this one minus 40 dB per decade. So, if you see this is minus 40, this is minus 20 dB, this also minus 40 dB. So, this will be approximately at the center of this one it is happening. Now, if you do the phase plot, it is minus pi and minus 40 here, here also minus pi. So, in between it will go like this, 0 at the gain crossover it will become maximum and then come here. So, we are interested this phase margin. If this from the basic control system theory, this phase margin, if we can adjust and away from minus 180 degree, then we can ensure the stability. So, let us find out, this is our omega c. At omega c, it will be here. So, let us find, usually this omega c will be placed at the center of these two. Log omega c is equal to C log of omega 2 plus log of omega 1 by 2, which is omega 2. Omega 2 is 1 by delta. This is omega 2. This is omega 2. And this is omega 1. Okay. Now, this will be equal to log of omega 2 omega 1 by 2. That is equal to log of omega 2 omega 1 raised to 1 by 2. Okay. So, omega c is equal to, from this one omega c is equal to root of omega 2 omega 1. We know omega 2 is 1 by delta, omega 1 is 1 by n. So, omega c will be equal to 1 by, okay, we can write it here, omega c is equal to 1 by root of Tn delta. Now, Tn we have to find out, Kn. So, and we know that omega c, the gain is 1. Let us go to the next page now and find out the values and then find out the phase margin. So, we have chosen omega c 1 by Tn away from 1 by delta, and we found omega c at the middle of these two, and we choose Tn is equal to omega del. So, here Tn is equal to 4 del, that is we got the Tn from the previous through equations from the previous example. So, we will apply that one also here. Now, at omega c, what is the gain of open loop gain? 20 log 0 omega c is equal to 20 log 1 0. That is the gain crossover frequency at the unity gain, correct? See, why this unity gain we are taking? We want our feedback loop which is connected to the controller input, where the reference and feedback is coming. We want the in all frequency variation, for all frequency variation of the input variation, input variations, the output, the feedback should follow the input. Okay? So, that is the thing. Now, from this the K4 and the controller gain can be found out. Let us see F0 j omega is equal to Kn Ra K1 by, that is the previous equation, K2 Km into 1 plus Stn. Here K4 we are actual constants we have put it there, then it will be Tn Tm S square into 1 plus S delta. Okay. Now, this is equal to Kn Ra by K2 Km K1 into 1 plus j omega Tn by Tn Tm into S j omega square, S j omega square into 1 plus j delta omega. Okay. At omega is equal to omega c, we know it. Now, we know it at omega is equal to omega c, and also Tn is equal to 4 delta. Omega c is equal to 1 by root of Tn delta is equal to, Tn is equal to 4 delta, substituting 1 by root of 4 delta square is equal to 1 by 2 delta. So, substitute this one here and let us find out what is the gain modulus. See, now, so previous equation we will copy it again here for clarity. Let us go to the next page. That is F0 j omega is equal to Kn Ra K1 by K2 Km 1 plus j omega Tn divided by Tn Tm j omega square into 1 plus j delta omega. Now, we know that at omega is equal to omega c, at omega c will be Tn is equal to 4 delta, we know omega c is equal to 1 by 2 delta, that we have derived last time. So, substituting this one, F0 j omega c should be 1. That will be equal to Kn into Ra K1 by K2 Km into root 5, that is mode we are taking. Tn is equal to 4 delta. Okay. So, this will be root 5 into delta by Tm j omega square s square, that is the one minus 1 happens s square into root 5 by 4. Okay. So, if you substitute this one in this 1 by 2 delta, from there we get this one. This finally will be equal to Kn Ra K2 Km K1 into 2 delta by T. Okay. From this one, what is Kn? Kn is equal to K2 Km by K1 Ra into Tm by 2 delta. Tn we got, we know Tn. Tn is equal to 4 delta. So, we got it. Now, from this equation, let us find out the phase margin, that is F0 at j omega c will be, this will be equal to Kn Ra K1 by K2 Km into 1 plus 2j by 4 delta Tm into minus 1 by 4 delta square into 1 plus j into 1 by 2. So, let us take angle F0 j omega. This is numerator. Numerator will be tan inverse 2. Because of the minus 1, you have minus pi and minus tan inverse 1 by 2. So, the phase margin, that is away from pi, it will be equal to tan inverse 2 minus tan inverse 1 by 2. This will be approximately around 36.8 degree. So, we got a very good phase margin. Now, from this one, let us go back to again our design. If you see here, our previous transfer, we have found out our Kn and Tn. Okay. Our previous transfer function omega Fs divided by omega R S is equal to K0 into 1 plus Tns into 1 plus T1s divided by Tn del S cube plus Tn S square plus K0 K1 Tns plus K0 K1. Okay. The effect of 0, we can we know from the current loop how to cancel it. See, when you have the speed reference happens, that is our omega Rs, you pass through another filter, that is 1 by 1 plus Tns, then again 1 by 1 plus T1s, or you can combine this one to one filter, 1 plus Tn plus T1s, then the feedback should come here. Then this part will go, the final transfer function will be like this. And here the Kn and Tn is already 4 del, Kn is we have decided according to our symmetrical symmetric optimization using graphical method. Let us design a controller. We have designed previous front end AC to DC converter also, we have designed it. Let us design a controller now. So, let us start a design. Design of a speed and current controller for a DC drive with the following specification. Specifications. Okay, rated power. Let us take 1. Rated power 300 kilowatt. Maximum rated voltage 460 V DC, that is our DC. Maximum rated current. (690 amps). Base speed let us say 500 RPM, and let us see the J is also we have found out. In the beginning earlier classes we have said how to find out J, moment of inertia with the motor plus load. So, moment of inertia J plus load is equal to 84 kilogram meter square. Let us see the for the machine the back EMF constant, that is C5. Okay, back EMF constant. See here we have that will be equal to, let us see represent this one as Km, that constant is equal to 8.5 volt second per radian. Okay, then again is not sufficient. Armature resistance Ra is equal to 0.02342 ohms and La is equal to 0.7026 millihenries. Let us take our converter we are using. Three-phase fully controlled thyristor bridge. Let us our time constant T1 for the tachometer, the filter, speed loop filter, T1 is equal to, that is tachometer speed, feedback, filter time constant. T1 is equal to 25 millisecond. Similarly, the current filter time constant. T2 is equal to 3.5 millisecond. Okay. Let us say our current maximum current is 690 amperes and maximum current limit. Our maximum current limit, that is, let us say current limit is equal to 1200 amperes. So, this is the maximum rated current. For momentary we can have rated current of 1200 we can give it. That is the maximum current limit. So, let us design our first with this one, our current controller. We know the current controller is equal to, that is our Kc is equal to previous equation Ta by 2 Kt K2 1 by Ra into, and we have product of the smaller time constant we have neglected, and we have approximated as Tt plus T2. This is the T2. This is the converter lag, and this is the current filter time constant. And we know that Tc is equal to Ta, armature time constant. So, we are using a pole zero cancellation there. Then we found out the transfer function 1 for theta is equal to 1 by root 2. We found out that Tc. Now, what is Ta from the previous equation? Ta is equal to La by Ra, that is 30 millisecond. Now, what is Kt, our converter Kt? Now, let us say we are designing with an analog circuit. So, we want to limit the maximum controller variable output should not go beyond plus 10 or minus 10. So, for the converter, when the input that control voltage is 10 volt, we want the required output voltage. Required output voltage, if you see what is the previous output voltage, we want maximum voltage of maximum rated voltage according to our rating 460 volts. So, the gain Kt is equal to 460 divided by 10. That means the moment the 10 volts comes and the maximum rated voltage of 460, the firing angle should go into such a level such that 3-phase fully controlled converter output should give 460 volts. So, Kt is equal to 46 now. Now, again speed controller output, see we the previous rating we said the maximum rated current it can go up to 1200 amperes, and here also K2 current gain, that feedback filter K2 is equal to the moment 1200 amperes current comes, we should get a output voltage of feedback voltage of 10. So, K2 gain is equal to 10 by 1200. See here 10 is in the numerator, because from the controller output we are getting 10, that is the filter, when the input is 1200. So, gain we have to reduce it like this. So, the gain K2 gain is 1 by 120. Now, converter time constant, we said the Tt is equal to, and we are using 3-phase fully controlled converter. So, a maximum delay of 60 degree or 0. So, we will approximate to 30 degree. 30 degree delay means 1 point, we know 50 hertz what is the period. So, 50 hertz is 360 degrees. So, for 30 degree it is 1.7 millisecond, okay, TTB. Now, T2 is already given, our filter time constant T2. T2 is equal to 3.5 millisecond. Now, with this one, our Kc, we can substitute these things in this equation and we can find out Kc. So, Kc is equal to Ta, 30 millisecond. So, 30 into 10 raised to minus 3 divided by 2 into kT, kT is 46, that is 46 into K2, K2 is equal to 1 by 120 into 1 by Ra, Ra we know it, Ra is at 0.02342 ohms. So, 1 by Ra is equal to 1 by 0.02342, okay, into T2 plus Tt plus T2. So, that means into here 1.7 plus 3.5, this is 3.5. 3.5 is the T2, this value, into 10 raised to minus 3. Here 10 raised to minus 3 is required because all are millisecond. So, this will come to, if you do it, it is 0.17. So, this gain we got, Tc is equal to Ta is equal to 30 millisecond. Okay. So, how do you realize the current controller? See, we know the PI controller. We will go back to our PI controller and we can design our values. See, this is our V in, that is our current reference is coming, okay, we will draw it here, current reference is coming, okay. And we said reference also we want to filter with the same time constant used for the current feedback, okay. So, we will use a filter like this, symbol filter we will use it, okay. Then same resistance we will give it. This is the I reference. I feedback after the gain reduction, we are putting the same filter here, okay, from the current transducer. After the gain reduction, same filter we will put it and feed it here, okay. So, we can choose this RC and this R. This RC based on our current filter time constant, that is 3.5 millisecond, and this also we can use 3.5 millisecond. Okay. Now, this will go to our PI controller. Minus, okay. Then our RF, okay. This is R1. This RF by R1, that is our P controller, that is our K2 value, not K2, this Kc value. So, how to control? We said we will put a resistance around 10 K port and we will put it like this. So, we will, by adjusting this one, we can have the gain of alpha gain, alpha we can adjust, we have derived this one previously. So, we can adjust the gain of 0.17. Then this will go to the integral controller, again R2, see integral time constant, we know Tn is equal to Tc is equal to Ts 30 milliseconds. So, Rc we can choose it that way. Okay. Then how to adjust fine tuning? Fine tuning you can do it again here like this with a potentiometer here and with a small resistance here, so that we should not short it while controlling. Okay, alpha you can controller. This will take care of our Tc. This is our, this will take care of our Kc, and this is the adjustment. Then here also this controller we have to limit it. Now P plus I, as I told before, this is our controller P plus I. Okay, this comes here. These are all same resistance RR. Then again from here. Okay. Then our limiting circuit. Okay. This I told, this I explained in the previous class. Then one more will be there. That will be positive. Okay. These two shorts here, and we will connect it with a small resistance. We will connect it here. So this output, one is negative. Okay. This will, we will put the references here for limiting plus 10 and minus 10 potentiometer. This we have explained. So this will go here, and this will also go here, output for controlling. This I have explained in the when we talked about the controller design. The same thing we can put it also here, so that capacitor should not go up plus 10 minus 10, and by independently controlling this alpha 1 and this alpha 2, we can control, we can fine tune the PI controller. Okay. The same way we can use it for the PI controller for the speed loop. Now let us talk about the speed controller. The speed control also we can realize in the same way we have realized the current controller. So the reference voltage here, speed reference, we will always limit between plus 10 and minus 10. The Tn is equal to 4 delta, that is equal to 4 into 2 sigma plus T1. T1 is our feedback time constant, sigma is our summation of the small time constant, the current loop. So this will be equal to 4 into 2 into Tt plus T2 from the converter, and the speed feedback filter time constant. Okay, Tn, and Kn is equal to, so we can use either symmetric optimization through equations or graphical method. So let us take this one from the equation method. This will be equal to Tm Km. This is the machine constant, K2 divided by 2 K1 Ra into Tt plus 2 T2 plus T1. See, we have to substitute this equation and we have to find out only. So Tt we know it. So we will derive Tt is equal to 1.7 millisecond. Then T2 is equal to 3.5 millisecond. And T1 is equal to 25 milliseconds. This is all given, our filter smoothing time constant. And Km, that is machine constant, that is 8.5 volt second per radian. See, units you should match, very important. And K2 we know it, K2 is equal to 1 by 120 is equal to 0.0083. And Ri we know, Ri is equal to 0.02342. Okay. Now, what is the filter gain K1? And we know that the maximum RPM of base speed RPM is 500 RPM. For 500 RPM, so 500 RPM, let us make in radians per second, that will be 52.3 radians per second. So, the moment 52.3 radians per second comes, we want a maximum voltage of 10. So, all our control is plus and minus 10. So, the gain K1 is equal to 52.3.10 volts, it will come to 52.3. So, it will be 0.19 K1 we got. So, let us write K1 is equal to 0.19. Now, substituting all these values, we get easily we will get Tm. Now, we have to find out Tm also required here, correct? See, because Tm is there, Tm. Let us find out Tm. Tm is equal to J into Ra by Km square. That Km is the C5 machine constant. So, that is equal, J is equal to, we know from the previous specifications, J is equal to 84 kilogram meter square. So, 84 into resistance 0.02342 by Km square, 8.5 volt per second square. This is 27.2 millisecond, and we found that this will have a unit of seconds, and we call as the electromechanical time constant. Okay. Now, substituting this one, what is Kn? Kn we can get it, that is very easy. Kn is equal to 27.2, substituting all the values in the previous equation, into 0.0083 divided by 2 into 0.19, 0.0234, 35.4 is equal to 6.12. Okay, we can take N is approximately equal to 6. Then we can do the fine tuning at the PI controller while running. Then Tn is equal to 4 into 2 into Tt plus T2 plus T1 is equal to 140 millisecond. See the assumption. This time constant for the loop for the speed is much higher than the current control loop. Okay. Now, with this one we can again design our speed controller. See, speed controller again the same way. We want the speed loop to be filtered by, we set what we set, we have to design the whole thing by, to avoid the overshoot at the numerator, that is we found it is 1 plus TNS plus 1 plus T1S. So, we can, the transfer function, if you see the numerator, you will have the 1 plus TNS plus 1 plus T1S. So, you want the reference to be filtered through this 2 filter, or we can approximately 1 plus Tn plus T1S. So, in complete speed loop we will write it. So, you have the speed reference. Okay. Then we will pass through a filter, symbol filter, that is R1C. So, RC is equal to, time constant is equal to Tn plus T1, we can use it. Okay. Then we will give to the same way operational amplifier minus this is our R feedback. Again we have to control the P part, fine tuning, that we can do it with this way. And the feedback after the gain reduction, that means we are giving a K1, again we are giving to this filter. Here the filter is R1 C2. R1 C2 should be equal to T1, that we are giving it, feed it here. Okay, feedback. So, you have to take care of the proper gain. This is plus or minus, we have to do it. So, gain through operation amplifier you can make the negative proper gain, and we can give it here. Then you have the integrator. We are not disturbing this one, we will make it Tn. Tn is equal to, we will say R3 C3. So, this is our Tn, and fine tuning we can do it here. Okay. So, this part again P controller, this is for the I control, independently we can control without disturbing the capacitor and R3. So, we do not want to disturb R3 because it will affect the input bias current requirement of the operation amplifier, and online changing C3 is very difficult. So, we will use this one. Now, from here finally it will go to our fine summing amplifier. Okay. These are same resistance, these are V0. So, V0 we want to limit plus 10 and minus 10 depending on what is our variation we require here. So, here again this we will take it from here. Okay. Okay. RR. Then you have the limiting amplifier, output limiting. So, here also we will use two operational amplifiers in open loop gain. Sorry, here it is the other way. So, here we will have the this way. Okay. This will be shorted, and we will use a small resistance which much less than R1. So, because this effect of this one should be faster than this one. So, one resistance we will put it here, some RL less than R. Now, this output we want to limit it. So, we will use it minus here. So, this is our resistance output. See, as I told before, see this output, whenever this is the positive limit, this is the negative limit, that is the lower limit. See, negative limit or lower limit can be 0 also. So, here we will again your plus 15 volt, here we will give to our negative limit, we will fix it minus 15 volt. If on 0 volt, we ground this one. See here, any time as I told before, this output goes on, let us see, this is plus 10 and this is minus 10. Okay. Whenever this output goes above this value, that is, this output is more than this value, what will happen? Output, this operation amplifier is in open loop gain. So, output goes negative, and this immediately this negative output will come here and reduce the gain. So, this open loop gain is so very high. So, this error will slowly decrease and it will go to, this error between these two are very minimal, such that this output will have the correct output to limit the output excursion to plus 10 only. Okay. So, it will be tracking the value here. If you see here, this output, this reference point will be tracking this value. So, that output will come to the required value. So, if you see here high frequency oscillation will be there, that you can avoid by using 100 PF here. So, this is our positive limit, that is why we have given this to the plus 15 volt. This is our negative limit. Negative limit can be 0 also. In that case, we can ground this one. So, what happens? Let us see this output, that is our this output. It goes more than 10 volts. More than 10 volts means this negative input is more than this value. So, because of the negative, this will go, because of the high gain, the output go negative, and this diode will conduct, okay, and this will appear here at the input positive terminal. So, output will be negative, output go to the positive terminal. So, this output will come down. So, it will come down and it tracks 10 volt because of the high gain here. So, this is, if you say we are giving proportional gain, open loop gain, and we said for steady state error in this case proportional gain, we said it should be, the gain should be very high. So, the steady state error will be 0. So, we are using open loop here. So, open loop, it has very high gain, 10 raised to 6 power gain will be there. So, this output will exactly follow this one, 10 volt, and it will be slowly tracking the output. So, if you see here, there can be a high frequency oscillation here. So, to avoid this one, we can use a small resistance 100 pf. Okay. This is for the positive case. Now, let us say the output is going negative, minus 10 volt. So, what happens? This is already minus, more than this minus 10. So, minus to minus 10 it will come here. This 10 will immediately go here and output will be raised to minus 10 volt. So, if it goes below this one, it will raise this one. So, as I told here also, we are using a P controller here to control the output. These are all feedback controllers, but we are using P controller with very high gain because operation amplifier is in the open loop gain. So, this error will, steady state error will be 0. That means, this output will exactly follow this one whenever the output goes above this value, and here also to avoid the this one the oscillation, we can use a 100 pf here. See, now here, but this way output we are controlled. The same output, same configuration, we can use it here also. PI control, that is, you have two operation amplifier this way, so that okay, you have the resistance here. We can have a small resistance here, it will go here, RL. Okay. Again we can have the same limits, positive limit, and you have the negative limit, and the output from here we can give it to this negative sides. Okay. So, we will ensure that whenever there is large error happens, this capacitor will never go to more than plus 10 or minus 10, and operation amplifier will never saturate. If it saturates, what happens? It will take longer time to come out of this one. So, and while running, fine tuning we can use it. We have already calculated our P controller, I controller based on our optimization techniques for with good damping, good stable, for stable output operation. See, we can use it, but fine tuning we can do it, get optimization, exact performance we can use it by fine tuning here, so that it will not lead to very large oscillations while tuning. Okay. This way we can do it. Okay. So, with this our DC motor speed control design, we will close it. Okay. Then we will study further, we go from the next class onwards.